Today's topic is all about learning to deal with radian measure. So our goals are that by the end of this lesson, we'll be able to describe what a radian is and then use radians to measure angles and to think in terms of radian measure, which is really important, and to convert between radian and degree measure, and then to solve problems involving angular velocity with radian measure. Okay, so what is a radian measure? So radians are used to measure angles. Okay, so up until now we've been working with degrees. Now we just have like a different unit of measurement. It's similar to like how you would have always grown up learning how to measure distances in meters, and then in high school you learn more about measuring things in feet. So they're different systems of units of measurement, but they're used to measure the same things, which namely is angles. So two things we're going to address first is how big is 1 radian, and then how many radians are in a full circle. So how big is 1 radian? So the definition of a radian is nice and neat. It's created, 1 radian is created when you take a circle and you take the radius of the circle, so however long it is, and you take this length and you kind of curve it around the outside of the circle like this. So we call that an arc length when it's like that rounded part there. So basically what this is saying is that the length of this and the length of this are the same. And of course this one, because that's also a radius, right? From here to here, that's a radius. From here to here, that's a radius. And then I'm just taking a curve that's the same length as those two radii and then putting it around the outside edge, okay? Okay, so the angle that's created when you do that, when you create this kind of, it's almost like a equilateral triangle, but not quite because the one side is rounded, then that's 1 radian, okay? That's how big 1 radian is. So there are a couple of things that we know about a radian based on this alone. This is almost the same as an equilateral triangle, right? Where each of these sides is 1 radian. It's just that we're taking this other side and we're making it curved. So this is like curved. In order to be able to do that, we know that we'd have to like shrink this side a little bit so that we have a little bit more room, right, for that part. So that means that this angle here, we know in an equilateral triangle, all 3 angles in a triangle have to add up to 180 degrees. So each one of these is 60, right? So that means that a radian has to be like a little bit less than 60 degrees. Just because it's like an equilateral triangle that we've kind of squashed in order to make this side curved. Cool? Makes sense, right? All right, so we have like an idea about how big it is. Now let's talk in general about the definition. So this is the definition of a radian. An angle, this theta represents an angle that's measured in radians. And it's equal to the ratio of the arc length. So the arc length is this curvy part. So that arc length is here, that curvy bit around the outside of the circle. So a radian is, or a measure in radians, is the ratio of that arc length to the length of the radius in that circle. Okay, so, and then the theta, the angle, is referring to the angle that's subtended here at the middle of the circle. We use that word subtend, which means like the angle that's created there at the center of the circle. So because it's a ratio, then we can see in this particular example where we have theta is the arc length, in this case is r, and the radius is also r. We know that radius divided by radius is 1. So this shows us like why or how it is algebraically that we connect this idea that this is how big 1 radian is, okay? Okay, so the next question that we're wondering about is how many radians fit in a full circle. So what I've done is I've colored the length of 1 radius, that arc length that's there, in red, and then I'm going to fit as many as I can around the circle and see how many we get. So there's 2, and there's 3, and 4, 5, and 6. And you can see that there's a little bit left over. So this little chunk that goes from here to here is like I don't have enough space for another radian. So that means that around the full circle, we're looking at a little more than 6 radians. So now what I want you to think about is what you know about the circumference of a circle. So hopefully you remember that the circumference of a circle is 2 pi r. And if we think about how big 2 pi is, you know, we've always kind of been comfortable with the fact that pi is approximately 3.14159, continuing on forever. So this is literally telling us that the circumference is about 6-ish times the radius. And that's exactly what we just saw, because that's what each of these was, right? That's what we were just looking at. That this is 1 radius, 2 radii, 3 radii, 4 radii, 5 radii, 6 radii. So we can see that there are a little bit more than 6 that fit all the way around the circle. So here's a much nicer diagram that kind of shows that. So just to kind of add to it, this sector of the circle is what that's called. This shows us 1 radian. Okay, that's what 1 radian looks like. So we can see that we can fit 6 of those, around the circle. And then with like a little extra bit. Okay, so that's 2 pi times the radius is the distance all the way around the outside of the circle. So here's our formal definition of a measure in radians. It's describing that ratio of the arc length created by an angle at the center of a circle to the length of the radius of that circle. Okay, so we have this equation right here. We're going to use this equation a lot. Okay, and I just want to point out, I mean, it should be obvious because this whole lesson is about radians, but this is talking about an angle in radians. Okay, so this equation doesn't work when we're talking about degrees because that's not what this is about. Okay, so 1 radian is equal to the angle subtended at the center of the circle by an arc length that's equal to the length of the radius. That's what we just talked about here, where this, and this would all be the same length. That shows us about how big 1 radian is, like this. And this angle is the same in all circles. So in class, if we were together in class, I would have each of you make your own circle and have, make sure that everybody's circle is a different size, and then we'd use pipe cleaners to find this. And you'd count how many radii could fit around the outside, and you would all get the same answer, a little bit more than 6. You'd all get the same size of that angle in the middle, which is pretty cool. Okay, so now we're going to formalize this a little bit. So we have, again, this kind of guiding principle behind us, that theta equals a over r, where a is the arc length, that's that curved part on the outside of the circle, and r is the radius, okay, of that circle. Okay, this is what those are referring to. And then this is like the angle in radians. Okay, so formally, how many radians are in a full circle? Well, we just heard that it's 2 pi, but we can kind of break that down this way. So we know theta is a over r. And if we're talking about a full circle, then we're talking about all the way around a circle. So we know that the circumference of a circle is 2 pi r. So we can plug that in as our arc length, okay? Because we're wondering how long is this angle? Like from here to here, how many radians is that to go all the way around? So that full arc length is the full amount of the distance around the outside of the circle divided by the radius would give us the angle in radians. And then we just simplify, okay, r divided by r, so we have theta is 2 pi. So all the way around a circle is 2 pi. So that means that half a circle, of course, is going to be pi. But again, we can look at it this way. We know that if we're talking about the arc length for half a circle, that would be 2 pi r divided by 2, because we're only talking about halfway around. And then divide that by the radius to get this, because this is our arc length. Okay, that's what that's referring to. Then we simplify. The 2 divided by the 2 goes away. The r divided by r goes away, and we're left with theta is pi. Okay, so this means all the way around a circle, up until now, up until grade 11, you've been thinking about all the way around a circle as being 360 degrees. Now we're living in this new world where we're calling that 2 pi. and you've always considered, to go halfway around the circle as 180 degrees. Now we're living in a new world where this is called pi. Okay, so the next thing that's really important that I want to talk about is thinking in radians, because you spent your whole life thinking of angles in degree measure, and now I need you to kind of think in a different language. In the same way that it's really inefficient to speak another language by translating constantly in your head, you want to ultimately get to a place where you can think in that language and then you can have a fluid conversation with someone. This is the goal, okay? So, if you've ever had a conversation with someone who speaks French and they are not really very fluent in French and they're constantly translating in their head, it makes the conversation pretty uncomfortable. So we want to get to that place where we can think in French, or in this case, think in radians. So we know that all the way around a circle is 2 pi. So let's just cut that circle up into different amounts so that we can get comfortable with how big each of those kind of segments is. So whenever we talk about a circle, or rather, whenever we talk about angles, we're generally going to talk about angles in the Cartesian plane. And as we learned about in grade 11, we always measure our angles from the positive x-axis going counterclockwise like this, okay? So in grade 11, you would have looked at this as 90 degrees, 180 degrees, 270 degrees, and then 360 degrees, right? Okay, so no longer. We are now going to live in the world of radians. So let's think about how big each of those angles is when we're talking in radians. So this is 0 degrees, but we're now calling it 0 radians. And if we were to go all the way around the full circle, this would be 2 pi radians. Okay, we know all the way around is 2 pi. So that means, of course, that halfway around is pi. So that means halfway to pi is pi by 2. This is how we often phrase a pi by 2. You could say pi divided by 2 or half pi, but often we describe that as pi by 2. And then over here, we can see that we have 1 pi by 2, 2 pi by 2, 3 pi by 2. So this is 3 pi by 2. And then 4 pi by 2, of course. But we know that 4 pi by 2 is something that simplifies down into 2 pi, right? Because 4 divided by 2 is 2. Okay, similarly, we could think of, like I said over here, I said pi by 2, 2 pi by 2. We know that 2 pi by 2 simplifies down to be pi as well. Okay, so the simplest way of phrasing each of these is going to be like the way that we're going to call them all the time. So this one up top is pi by 2. That's a quarter of the way around the circle. Halfway around the circle is pi. 3/4 of the way around the circle is 3 pi by 2. And again, you can break that up into thinking how many pi by 2s are there. There's 1, 2, 3 pi by 2s, okay? And then all the way around is 2 pi or 4 pi by 2. Okay, so that's breaking up into pi by 2 segments. Now, what if we break this up into a different number of segments? What if we break it up into not just the 4, but rather we cut each of those again in half. So we're cutting the entire circle in 8. So again, we're starting here at 0 radians. So we can see that we've cut this from here to here. We know that this is pi radians, right? So if we're cutting this into 4 pieces, then each of these is pi by 4, right? Because we've taken that pi, we've divided it up into a quarter. So here's 1/4 of pi, which is pi by 4, and here's 2/4 of pi, or 2 pi by 4. But we know that 2 pi by 4 simplifies down into pi by 2. And we have 3 pi by 4s right here. And that can't simplify, so that's where we're going to leave that. And then 4 pi by 4 like this. So that would be a full pi, right? Because we know that that would simplify down into just pi. Okay, we can continue like this. So that's 5 pi by 4, 6 pi by 4, 7 pi by 4. And then, of course, all the way around would be 8 pi by 4. And we know that 8 pi by 4 simplifies down to be 2 pi. And 6 pi by 4 simplifies down to be 3 pi by 2. And hey, that's what we said is that 3/4 mark, like 3/4 of the way around the full circle, was before. So again, kind of talking about those kind of key places, this quarter of the way around the top half of our circle is pi by 4. We know that up at the top here we have pi by 2, 3 pi by 4 over here, 4 pi by 4, which is just pi, 5 pi by 4 over here, 6 pi by 4, which is just 3 pi over 2, 7 pi by 4, and then 8 pi by 4, which is really just 2 pi. So now the next thing is, what if we cut our circle into 6 equal segments? So we're looking at how big each of these sections is, again starting at this 0 mark and working our way around. So we know from here to here, that's pi radians, right? So if we're only going from here to here, that means we're only going 1/3 of the way to pi. So this is pi by 3, okay? And then to go to the next marker, this is 2 pi by 3s, right? Because we have one here and then another one here, so that's 2 pi by 3s. So this is 2 pi by 3. And then next, this one here is 3 pi by 3, which is the same thing as just pi, right? 3 pi by 3 is like 3 pieces that are the size of pi by 3. We continue on. We can see that this is now 4 pi by 3, 5 pi by 3, and 6 pi by 3, which is the same thing as 2 pi. Awesome. So again, we have some key markers here. We need to know this pi by 3, this 2 pi by 3, this guy is just pi, 4 pi by 3, 5 pi by 3, and then of course all the way around is just 2 pi. So now, what if we take that circle, cut up into 6, and we cut each of those pieces up in half again? Then we know that we get our total circle cut into 12 pieces. Okay, so again, starting here at 0, then that means that all the way from here to here, this would take me to pi. And so just one of those sections, just one guy right here, would be pi by 6. Because all the way across from here to here would be a full pi, and we're taking that pi, which is just the top half of the circle, cutting it up into 6 pieces. So this is pi by 6, 2 pi by 6, 3 pi by 6, 4 pi by 6, 5 pi by 6, and 6 pi by 6, 7 pi by 6, 8 pi by 6, 9 pi by 6, 10 pi by 6, and 11 pi by 6. Okay, now of course some of these can be simplified. So this 2 pi by 6 is really just pi by 3, right? Because the 6 and the 2, they can simplify to give us just a 3 on the bottom. We know the 3 pi by 6 is really just pi by 2. We know that 4 pi by 6 is just 2 pi by 3. 5 pi by 6 can't be simplified, so that's one that we need to know. 6 pi by 6 is equal to pi. 7 pi by 6 can't be simplified. 8 pi by 6 can be, though. That's 4 pi over 3. 9 pi by 6 can totally be simplified to 3 pi by 2. 10 pi by 6 can be 5 pi by 3. And 11 pi by 6 can't be simplified because 11 is prime. And then, of course, all the way around would be 12 pi by 6, which is the same thing as 2 pi. So again, we have some of these guys that we need to know. This, just one of those pieces. If we cut the entire circle up into 12, each of those pieces is pi by 6 big. And then we have the pi by 3 would be like that 2 of those pieces together, 3 of those pieces, 4 of those pieces, 5 of those pieces would be 5 pi by 6. 6 of those pieces would be pi. And then 7, and then 4 pi by 3, 3 pi by 2, 5 pi by 3, 11 pi by 6, and 2 pi. So I know that seems like a lot, but it takes time to learn to think in a new language. But I hope that just doing this exercise shows you that when we're thinking in radians, we're just talking about cutting up a circle. Okay, so how many pieces are you cutting up that circle into? If we know that half the circle is pi radians and the full circle is 2 pi radians. So we can kind of work with that. you will get comfortable with these new measurements over the course of this unit. So the next thing to talk about is converting. I generally want you to be thinking in radians whenever possible, but sometimes we do have to take a measurement that we already have in degrees and be able to convert it into radians and vice versa. So to convert it, what we're going to do is we're going to think about proportions. So we know that all the way around the circle, 360 degrees, is 2 pi radians, and that halfway around the circle, 180 degrees, is pi radians. And we're going to kind of use that by talking about how much of a circle is a particular angle measure occupying. So for question A there, 40 degrees, we want to know how big that is in radians. So what we're thinking about is like 40 degrees is some portion of a full circle, right? And we want to know how much of a portion of a full circle is that in radians. Okay, so I'm setting up this equivalent fraction here, this proportion. And you can see that we have here like 360 degrees is all the way around the circle, and 2 pi is also all the way around the circle. So that kind of works with us here. And so 40 degrees is like a portion of that. We want to know what is that portion considered in radians. So now we just have an equivalent ratio that we can solve. Of course, well actually I'll do this one here with this 360 and you'll see how it will simplify. So to actually solve this, we know we would multiply both sides by 2 pi in order to isolate x, leaving us with 2 pi times 40 over 360 degrees. These are both degrees. And this equals x. Okay, so we can simplify a little bit. Notice that this is the 2 and the 360. I can divide those. So I have pi times 40 over 180. And that's equal to x. And then from there, I can simplify the 40 over the 180. The reason that I did that this way is because I want to make a connection about this pi over 180 that just happened here. So we have pi times 40 over 180, and 40 over 180 simplifies into 2/9. So this is 2/9 times pi. So that's what that measure would be. 40 degrees in degrees would be 2 pi by 9 radians, or 2/9 of pi, or 2 pi divided by 9 radians. And let's do our second example, and then hopefully you'll see commonality. So I hope you can see, firstly, that when we looked at that before, I used the 2/9, or sorry, the 2 pi by 360 over the pi over 180. But you'll see like that it would have just been easier if I had used pi over 180. So using that as my base proportion that I'm going to kind of build from is always like a good idea, just because it's less simplifying in the end. Okay, so a similar kind of thing. You have 135 degrees here. That's some portion of pi, of 180 degrees. Okay, so those are both degree measures. We want to know what portion of pi is that, so that we have an equivalent proportion, but in terms of radians instead of in terms of degrees. So to rearrange, I multiply both sides by pi, and we get 135 pi over 180 is equal to x. And we simplify from there, so 135 out of 180 is 3/4, so this is 3 pi by 4 is equal to x. That's how many radians 135 degrees is. Great. Again, I want to point out that what we ultimately ended up doing was taking 135 degrees and multiplying it by pi over 180. Notice that that's what we did here in the first example as well. So generally what we have is when we convert from degrees into radians, what we're doing is we're multiplying by pi over 180. Okay, what that does is it's kind of like in physics how you cancel units. So we want to cancel the degree amount, so we put the 180 degrees on the bottom, so it cancels out with whatever degree amount is on the top, leaving us with something that's in terms of radians. And multiplying by pi over 180 is really just the same thing as multiplying by 1, because, as we talked about before, 180 degrees is pi radians, okay? So when we multiply by pi over 180, this is really just multiplying by 1. So we're not changing the value is what I'm trying to say here. Okay, question C. So 5 pi by 3 radians into degrees. So let's go the other way. So 5 pi by 3 is some proportion of a full pi, or you could say out of 2 pi, it doesn't really matter. We want to know what proportion out of 180 degrees is that, and kind of solve from there. So this time, to isolate x, I have to multiply by 180 on both sides to keep it balanced. And that leaves me with 5 pi by 3 times 180 divided by pi, because there's a pi on the bottom. Now I can simplify. So I have pi on the top, pi on the bottom, those go away. And then I simplify. 5 times 180 divided by 3 is 300. So this is equal to 300 degrees. Again, I want to point out that this time, what we ended up multiplying by wasn't pi over 180, it was 180 over pi. Let's look at the last example and see how that one shakes down. So 5.8 radians, we want to know how many degrees that is. So 5.8 radians is some proportion of pi radians, or 2 pi radians, doesn't matter which one you use. And we want to know how many degrees is that. So that would be some equivalent proportion of 180 degrees. Again, because pi radians and 180 degrees are equivalent. So we rearrange and solve the equation, multiply both sides by 180 degrees. And notice here that ultimately what this is doing is it's taking the original amount in radians, multiplying it by 180 over pi. And we get 180 times 5.8 divided by pi is equal to x. And now we go to our calculators. 180 times 5.8 divided by pi is 332.3-ish degrees. So again, okay, I'm going to go back to this idea. I just want to point out this commonality here, that when we were converting from radians into degrees, what we did is we multiplied by 180 over pi. Okay, so that's like a good strategy. Okay, now the next thing I want to think about before we move on is reasoning, okay, to decide if the answers that we got make sense. So let's actually start at the bottom here. And question letter D. So 5.8 radians, we know that because all the way around the circle we said was a little bit more than 6 radians, because that's 2 pi radians, we know that that's like a little bit over 6. We know that 5.8 is pretty close to that, right? So we must have like a pretty decently big angle to be over here at that 5.8 mark. So when we get an answer of 332.3, I should put degrees, then we can gauge, is that reasonable? Does that make sense? Is that angle 332 degrees in about the spot that we would expect? Yes, it is. Okay, we're pretty comfortable with degrees, so hopefully you know that, like, because it's past that 270 mark, that would be in this quadrant, so we feel pretty good about that. Same thing over here. 5 pi by 3 means if I were to take pi, which is the top half of the circle, and cut it into 3 pieces, so there's pi by 3, there's 2 pi by 3, there's 3 pi by 3, so I want 4 pi by 3, 5 pi by 3 is over here, like this. So again, I'm in that 4th quadrant, so it makes sense that this should be about 300 degrees, because we know that that's where 5 pi by 3 is. Same thing over here, 135 degrees. We want to check our answer. So we got that it's 3 pi by 4. So we know that 3 pi by 4 means that if you took pi and you cut it into 4 pieces like this, like 4 equal pieces, that we would have 1, 2, 3 would put us here. And we know that that's where 135 degrees is, because hopefully you're pretty comfortable with the fact that 135 degrees is like 45 and 45 and another 45, right? So that's 135 degrees, which is the same thing as 3 pi by 4. Okay, So this one's like a little harder to gauge, but not so super crazy, because we know that 2/9 is a little less than a third. So it's like 0.22222 forever and ever and ever. So we have just like kind of a rough idea of how big that is. So 2/9 pi is like a little bit less than a third of pi. So if we were to take pi, cut it up into 3 pieces like this, like 1, 2, 3 equal pieces is what I'm envisioning. We know that 2 pi by 9 is like less than one of those, right? Less than the first one. So that feels pretty good because this is 40 degrees. We know that 40 degrees is totally less than a third of the way to 90 degrees. Less than a third of the way to 180 degrees, because this is 180 degrees here. And we know that that's like a little bit less than half of the way to 90. Okay, so to sum it all up, if we're going from radians into degrees, then what you want to do is you want to multiply by 180 over pi, because what will happen is typically a radian measure will have pi in it, not always, but sometimes. So then whatever pi is on the top of this amount is going to cancel out with the pi on the bottom, and we'll be left with an answer in degrees, okay? So, and then if we're going the other way, if you're going from degrees into radians, then you're going to multiply by pi over 180 for the same kind of logic. So the degrees are going to cancel out on the top and the bottom, and you'll be left with an answer that includes pi, which is nice. All right, so the next thing I want to kind of build on is going back to this idea of 360 degrees being equal to 2 pi radians. So if we chop that in half on both sides, so divide by 2 on this side, divide by 2 on this side, then that leaves us with 180 degrees equals pi radians. Okay, so I have two different ones here, so let's focus on one at a time. So 180 degrees is equal to pi radians, which again we're comfortable with because we know halfway around the circle is 180 degrees. We know that that's also the same thing as pi radians. Now, if I were to rearrange this equation so that I can figure out how big 1 radian is, then to do that, I would have to divide this side by pi. And then, of course, because it's an equation, I have to keep it balanced, I have to divide the other side by pi. So pi divided by pi is 1. So this is 1 radian is now equal to 180 degrees over pi radians. And this is nice because this is something I can type into my calculator, and I can get an actual measure for the size of 1 radian, and it's about 57.3-ish degrees. That's about how big 1 radian is, okay? And that's consistent with what we predicted at the beginning of this lesson when we talked about how it's basically just like a little bit less than 60 degrees, because it's kind of like 1 radian is kind of like creating an equilateral triangle where one of the sides is curved. So this just gives you an idea of how big 1 radian is, and then we can look at the same thing for degrees. So I started in the same place, 180 degrees equals pi radians, but this time I want to figure out what 1 degree is. So I divide this side by 180 degrees, so I'm left with 1 degree on the left, and divide this side by 180 as well. So we're left with pi over 180. This is equal to 1 degree. So 1 degree is pi divided by 180, which is like a really small number. So 1 degree is about 0.017. The point of this is just to give you an idea about how each of these units of measurement sizes up in the other system. The reason that I point this out is because a lot of times students find answers that are really small, like when they're converting values, they get like 0.09 as an answer, and they think it's wrong just because you're not used to working in angles that are that small, like with numbers that are that small, but that's actually not crazy, given that 1 degree is 0.017 radians, just so to give you kind of a heads up. All right, so next I have a different kind of example. So a circle of radius 25 centimeters has a central angle of 4.75 radians. Determine the length of the arc that subtends this angle. Okay, so basically what I have to do to answer this question is I have to look at something that involves all of these different ideas. So we have information about the radius, we have information about that angle at the center of the circle, and we're being asked about the length of the arc. Okay, so this is the arc length. So I hope that that makes you think of that equation that we talked about at the beginning of the lesson, which is kind of like the definition of what radian measure is, which is the ratio of the arc length to the radius of the circle. So I'm going to kind of fill in everything that I know. So we know that the central angle is 4.75 radians, so that 4.75 goes in where the theta was. We don't know what the arc length is, that's our unknown, but we know that the radius is 25. So now we have a really simple equation that we just need to rearrange and solve. So I'll multiply both sides by 25, and we get an answer for the arc length, which is 118.75. And then now we have to think about what units this is in. So because the radius was in centimeters, this arc length has to also be in centimeters. So we have, therefore, the arc length would be 118.75 centimeters. And again, it's really important that we think about whether or not this is a reasonable answer. So let's just kind of sketch it out based on how big we think 4.75 radians is. So here's 0 radians. It's also 2 pi radians if we go all the way around. We know that 4.75 radians is a little less than 5. So let's get a different color. So we have like each radian is like a little bit less than 60 degrees. So I know I'm going to fit a little bit more than 3 of them in here. So just kind of like roughing this out. So we have like 1, 2, 3, 4, 5, 6 and a bit radians to go all the way around the circle. So 4.75 radians would be 1, 2, 3, 4, and then most of this way here. Okay, so we're in kind of this region to look at what 4.75 radians is. So now this whole question is about how big is this arc length? Like how long is this black line from here to here, or black curve rather, from there to there? How long is that if the radius of this circle is 25? So if the radius of this circle is 25 centimeters, does it seem reasonable that this curved distance would be 118.75? And I think so. I would say yes, because we know that 4 of those would take us to 200, and we are further than 4 of that, kind of like that many pieces going across. This next example seems like it's the same kind of question, which it almost is. So let's go over it. A circle of radius 2 meters has a central angle of 120 degrees. Determine the length of the arc that subtends this angle. So again, just like last time, I noticed, okay, well, this is asking or giving me information about the radius. It's giving me information about the angle at the center of that circle, and it's asking me about the arc length. So that makes me think of this equation, theta is equal to A over R. If I start plugging stuff in, so I know the radius is 2, I know that I'm solving for A, so that stays as my unknown, and then here's my angle, so 120 degrees. This is the part that I need to be aware of. I can't put the 120 degrees in this spot, okay? Because this equation only works if this angle is in radians, okay? So the first thing I have to do is I have to convert that 120 degrees to radians. So I could do algebraically what I had shown you before, but 120 degrees is an angle that we're pretty familiar with, hopefully. So we know that 120 degrees is obtuse, it's like here. And we know that it's 2 60s, right? If this is 60 degrees and then this is another 60 degrees, then we know that all the way from here to here is 120 degrees, right? Hopefully you also know that if I added one more 60 degree segment, or sector rather, I would get to 180 degrees. Now, thinking of this in terms of radians, all the way across from that beginning point to this end point would be pi radians. And what we just effectively did is we took that pi and we chopped it up into 3 pieces. So this is 1/3 of pi. So 2 of them would be 2/3 of pi, or what we call 2 pi by 3. So that means 120 degrees is equal to 2 pi by 3. Of course, what I could do is I could do the thing that I showed you a moment ago, which is, set up my proportion. 120 degrees is what proportion of 180 degrees. That needs to be equivalent to the proportion of x over pi radians, and then just rearrange and solve the equation from there. You can totally do that, but hopefully you get to a point where there are some angles that you will recognize and be comfortable with the fact that 120 degrees is 2 pi by 3. So now we're ready to use that measure of that angle in our equation because it has to be in radians to be able to do that. So this is 2 pi by 3 radians is equal to a over 2. We multiply both sides by 2, and we get 4 pi by 3 is equal to the arc length. Now the arc length is in centimeters, so our final answer needs to state that. And I know that it's weird to talk about a length in centimeters as 4 pi by 3 centimeters, but that is an exact answer, so it is the preferred answer. But if you want, you can use your calculator, do 4 times pi divided by 3, and then you get, this is like about 4.19 centimeters. Okay, just so you have like a rough idea of what that actually means in real life, in a context that's comfortable for you. So another kind of common example is a question that's about angular velocity. So here's one about the London Eye Ferris wheel, which has a diameter of 135 meters and completes 1 revolution in 30 minutes. So the first part is just asking us, what is the angular velocity in radians per second? So the idea of angular velocity is talking about how fast something is rotating, okay? So how many degrees or radians is it covering in a span of time, okay? So instead of talking about the distance that it's traveling, it's talking about how far it's rotating. So because it tells us in radians per second, that kind of gives us something to work with. So we know our answer is going to be structured this way, radians per second. So we know that this is talking about like what angle is happening, or are we covering rather, and then we know that seconds is all about time. Okay, so that means that we're going to use the information that we have, which is the fact that 1 revolution takes 30 minutes to do. So that means that 1 revolution is 2 pi radians. Okay, and we know that that takes 30 minutes. So 1 revolution happens in the span of 30 minutes. Okay, so this leads us to this statement, or this fraction rather. So 2 pi radians over 30 minutes. This is our speed in radians per minute. But the question is asking us for radians per second, so we have to change the minutes into seconds. So we know that there are 60 seconds in every minute. So we have 30 minutes times 60 seconds is 1800 seconds. And we're covering 2 pi radians in that time. So our speed is 2 pi radians per 1800 seconds, but again, it's weird to describe a speed like that, so we should totally simplify that fraction. So that gives us pi by 9, pi radians over 9 seconds is one way to write that exactly, but if you like, you can convert that to a unit rate and get a final answer all the way down to an approximate 0.0035-ish radians per second. Okay, so you have a unit rate at the end there. Okay, so that's question A. Now, question B asks, how far has the rider traveled 10 minutes into the ride? So 10 minutes into the ride, let's think about that. If we can go all the way around the circle in 30 minutes, but we only want to know what's happening in 10 minutes, then we know that this is only a third of that, right? So if we divide that time by 3, then we should be able to divide the amount of radians that we've covered in that span as well by 3. So we have 2 pi by 3 radians that we're actually covering in the span of 10 minutes. So now we know what our angle is, okay? So therefore, in the span of 10 minutes, we're traveling 2 pi by 3 radians. Awesome, so we can use that. Now, the next thing is asking us how far the rider has traveled 10 minutes into the ride. So again, if we can just like draw a Ferris wheel and kind of picture it for a second. So traveling all the way around would be 2 pi, but we are only going 2 pi by 3 radians in that span of time. So that means that we're doing 2/3 of pi, which is about here. I'm just going to grab a different color. About here, right? 2/3 of the way across here. So this is how far we're traveling in the span of that time, how far we're rotating rather. So we're wondering what is that actual distance? So we need something that relates the angle that we're traveling to the distance that we're traveling around a circle, and that equation is again theta equals A over R, which is the angle is equal to the arc length over the radius. So what we're actually looking for here, how far has the rider traveled? This is the arc length, because the arc length is a distance around the outside of a circle, right? It's a part of the circumference. Okay, so the arc length is a distance. Okay, so that's kind of what we're looking for. Now we know that 2 pi by 3 is our angle. The arc length is the thing that we're looking for, and the radius we know is given to us at the beginning of our problem. So we know that the diameter is 135 meters, therefore the radius has to be half of that, which is 67.5 meters. So we plug that in, and we rearrange our equation to solve. So multiply both sides by 67.5, so we get 135 pi over 3 is equal to A. We can simplify 135 divided by 3 is 45. So there's an exact answer. So therefore, the rider has traveled. Notice that my therefore statement is always in the context of the problem. Has traveled 45 pi, what is our unit? Meters in 10 minutes. And again, if you don't like having your answer in that beautifully exact form, you can calculate 45 times 3.14, 159, etc., using your pi button in your calculator, and find that that's approximately 141.4 meters.